All right, so let's talk about the average value of a function on an interval from a to b. So in the last video, I talked about the mean value theorem, and that theorem essentially guarantees the existence of some point inside the interval a to b, which we call the value c, which is between a and b somewhere, some point where the value of the integral was equal to the area of a rectangle formed at height f of c. And f of c is the average value over here. So I've changed it. So instead of writing f of c, I've just written f subscript ave. This is just notation which means f average. Okay, and the formula we would get for that is just the formula from the mean value theorem solved for f of c. So we divide both sides by b minus a. That's what the 1 over b minus a is doing here. And then we're just obviously taking the integral. So in this formula, the value of c is not going to necessarily be obvious. Like the value of c is not going to come from this formula. But what we will get is the value f of c. And we could therefore then set the function equal to that value and then calculate c if we wanted to. Anyway, this is useful for finding averages and the average value of something which is changing continuously. So I want to do an explanation. This is not exactly a proof, but it is an explanation of why this is what it is. Okay, so let's think about the average of a bunch of numbers. If you have a bunch of numbers, the average of those is you add them all up and then you divide by how many there are, right? But if you have a quantity which is changing continuously over time and you want to calculate an average, what are you going to do? Well, let's draw a picture of that. Here's our function, right? And let's say here's our interval, a to b. Here's a, here's b. What you can do is you can imagine that you are like a point traveling along this curve here, and what you're going to do is you're going to sample the y coordinates. So you're going to take a sample of your height at regular intervals. So let's go ahead and split this up into some subintervals. Okay. Burp, derp, 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 derp. There we go. Okay, so then if you're taking right-hand intervals, you're taking the right-hand endpoints of the subintervals as your sample points, then you grab points like this. You grab a point there and there, and there, and there, and there, and there, and there. And you'd be adding up all of those you'd be adding up all of those heights, right? And then you divide by how many there are. So let's say that there's going to be n sample points that we take. And those are called C1 ... to Cn. Okay, so this would be like C1, C2, ... and then down here, B will equal Cn at the end. Okay, so there's our n sample points. So what we can do to approximate the average value, okay, to get an idea of what the average value of this function is going to be, we can add up, summing from I equals 1 to n, all of the function values at the sample points, so f of ci, right? So we add up all the f of ci's. Those are going to be these heights, right? The y coordinates. We're adding up all these heights together. Then we want the average, right? So then we'll divide that by the number of them that we added, which would be n. So we have 1 over n. That's dividing by n. So this is going to be approximately, not exactly equal to, but approximately our average value, right? Because the reason it's approximate is that we don't really know for sure exactly what's going on in between our sample points, right? Like, we don't know if the function goes straight or if the function kind of like wiggles up. You know, maybe the function shot up suddenly and then came back down again. And we weren't able to capture that information in our sampling, right? Because we missed it. It was in between measurements. So what we can do is we can take the limit of this as n approaches infinity to calculate the exact average value. Okay, so this is kind of very similar to the notion of adding up a bunch of areas of rectangles. This should sound familiar, right? It's kind of a similar idea here, except we're not really adding up rectangles. We're adding up function values and then dividing by how many there are. So, so if we take the limit as the number of sample points increases to infinity, then we will be able to capture all of the information about what's going on in between, you know, all of the little wiggles and stuff that might be happening in between. We're going to get all of that because we're going to be taking measurements like infinitely often like at every single moment between A and B, right? So it'll converge on, the limit as, n increases to infinity, it'll converge on the exact average value. This calculation will. Okay, so this is great, but how do we get from here to here, right? Well, you can already see there's a lot of similarity between this formula that I've come up with for calculating the average versus this integral, because the integral is defined as a limit of a sum, right? So if we can just take this and manipulate it a little bit into the format of an interval, of an integral, then we might be able to obtain this formula from my calculation here. And all that's missing, actually, all that's really missing is a delta x on the end. Like right over here, we should be, to get the integral, we should be multiplying the function heights by the widths of the subintervals. So we need a delta x. But what we got to do here is get inside here and multiply by delta x divided by delta x, because we need it to still equal what it did before. We're just going to do some algebra manipulation on this. So what I have now, what I can do now is inside my sum, I can say f of ci times delta x. That's the numerator, right? I'm going to keep that one inside the sum, but the division by delta x, I can actually factor that out of the sum, right? Because delta x is not dependent on I. Delta x is independent of the I. It's the same because all the subintervals are exactly the same width. So I can factor that out and put it on the outside. Oh, I forgot my n. There's also a times n inside here. My bad. That's from there. Okay, so now let's use the fact that delta x is calculated by taking b minus a and dividing by n. So if we take that and substitute it in here, what do we get? Well, let's just do that here. N times delta x is going to be n times b minus a over n, and you can see the n's are going to cancel out. So all that we have left inside here is now 1 over b minus a. And then we're summing up I equals 1 to n, the f of ci times the delta x. Now the 1 over b minus a, that's going to be constant because a and b are the endpoints of the interval. Those aren't changing, especially not as I changes, and definitely not as n changes either, right? A and b are held constant in the limit. So the 1 over b minus a can factor out. We get the limit of the sum f of ci times delta x, and this limit of the sum, that is our integral from a to b of f of x dx. So that brings us back to the formula, and that essentially proves the average value formula. Okay, it's pretty close. It's like I left out some details, but I wanted to show you this because it really connects the intuitive idea of average, adding up a bunch of numbers and dividing by how many, and then connects that via this step here of multiplying and dividing by delta x. We can then massage that formula into the form of a definite integral. And what we end up with on the outside is not dividing by how many there are, but rather dividing by the length of this interval, because we had to take the number n and ended up multiplying it by the width delta x, which produces the full length a to b. So anyway, I like that. I think this is a nice little connection so that the average value of a function does not seem that different and that disconnected at all from the average value of a bunch of numbers. So okay, in the next video, we'll go ahead and do an example of applying this formula.